Today we'll be introducing the Jovian planets. The Jovian planets, named after the god Jove, as you'll see in the video, are the four outer planets. So here's a comparison of them. The largest of the Jovian planets by far is the first one, Jupiter. Then we have Saturn with its very distinguished ring system. Then finally Uranus and Neptune. So we're going to look at each one of these and look at similarities and differences. So just some statistics on these before we watch the video. I guess the video is linked on the next slide after this. But just some statistics. First, the distances. How far are they from the sun? What difference does it make? These all had to form beyond the frost line to be able to hold on to the hydrogen gas and the things that we consider volatile. So things that have low melting temperatures. Things closer than the frost line could only hold on to the high temperature things. So the composition of these is very different because they're far enough away. So Jupiter, about 5 times as far from the sun as we are. It goes around the sun basically once every 12 years, and its mass is 318 Earth masses. Okay, that's a very big mass. We think of the Earth as pretty massive, right? But Jupiter's 318 times the mass. Its average density, 1.3. That was something you had to do for the last homework, was calculate that number. One person had a different number. I still gave him credit for that. It was just a calculator error. But you had to calculate that density by taking its mass divided by its volume. However, the density is not uniform. In the Earth, the density is not uniform. It's believed that the density at the very core of the Earth is about 17 grams per centimeter cubed. So that's the average for the Earth is 5.5, and up in the crust it's around 3.5. So it's much more dense in this core of the Earth. They believe, and remember that is by computer modeling, nobody's been there to test it. They believe that Jupiter's is almost twice that at 31 grams per centimeter cubed. So it's really compacted in Jupiter. So that average density is taking into account a whole lot of very low density material to mix in with that very high density in the core. And then you have the rotation rate, how long it takes to do one rotation. It takes basically 10 hours for Jupiter to do one rotation. That's less than half the time it takes for the Earth to do one rotation. Considering that it has a radius that's much bigger than the radius of the Earth, that means that the surface is going very, very fast compared to the surface of the Earth. The flat earthers would say that it's impossible for any gas to stay on Jupiter. It'd have to all be flung off. Jupiter must be flat too, right? Fits with their logic. Go out to Saturn, and just for comparison, you can see Saturn is about 1/3, a little less than 1/3 the mass of Jupiter. Still 95 times the mass of the Earth, but it's much smaller in terms of mass. Also, in diameter, it's a little smaller. But notice the drop in mass is much bigger than the drop in size. The result means that the average density is very low for Saturn, much lower than the density of water on Earth is. And yes, rotation about the same, 10.7 hours for one rotation. So very clearly going quickly. Because it has a much lower mass and spins so rapidly, it is flattened out more. More mass, gravity holds it into a more spherical shape. So Saturn is our most oblate planet. And by oblate, we mean instead of spherical, it's stretched. Remember, a circle that's stretched we call an ellipse. A sphere that's stretched is called an oblate spheroid. So oblate is the stretching of the sphere. Okay, then we have Uranus, or Uranus. Notice it's about twice as far away as Saturn. So it's a big jump in distance. You double roughly going from Jupiter to Saturn, double roughly again going from Saturn to Uranus. And you go a big step, go out to Neptune beyond that. So these last two are very far away. Uranus and Neptune are a lot like Jupiter and Saturn, but they're a lot different as well. In fact, we break these up we call the upper two the gas giants. And then the lower two, I don't know if any of you are fans of the Marvel movies, but one of the questions they ask is, where are the ice giants? Here they are. Uranus and Neptune are the ice giants. So now, if anyone asks, but where are the ice giants? You're right. They're out there. They're, somewhere between 20 and 30 astronomical units away. But they're not far. Okay, so if we look at those, we see their densities are going up again. So Saturn was the lowest. Uranus is about the same as Jupiter, and Neptune is higher density than that. And their rotation rates are a little bit slower than Jupiter and Saturn. And of course, their masses are much, much less than Jupiter and Saturn, but much, much greater than the Earth's. What are they made of? Well, all we really can do is look at the gases in the atmosphere. Saturn and Jupiter, we have actually sent probes to explore and measure the gases in the upper atmosphere. The probe in Jupiter, it probed for about 200 kilometers or 1 hour's worth of data collection as it descended into the atmosphere of Jupiter. So we do have direct measurements of the outer atmosphere. What's going on closer is all then going to be, I don't want to say conjecture, but it's hypothesized based on what we see of elements and abundances elsewhere. Yeah.
Would it be possible to create an instrument that could land on the surfaces without getting crushed by the pressure?
Well, first, remember, there is no such thing as a surface for these planets. It gets thicker and thicker, but there's no surface. So, since there's no surface, you can't really answer yes to that. You could create something that goes maybe deeper than the probes they did, but eventually it's going to get destroyed.
I was thinking this is the core or something like that.
Well, yeah, the core is solid, but yeah, you're never going to be close to there. Yeah.
So then, when they first entered that planet, is it just like you're going into gas? Like you just see gas everywhere and you just keep going into more gas and more?
Yeah. So basically think of it similar to skydiving into Earth, except for it gets thicker and thicker. So if you're skydiving into Earth from beyond the atmosphere, you'd be coming in and there would be nothing resisting your arms, right? And then you start feeling a little more and a little more. And then, of course, you would have a big splat at some point on Earth. Whereas with these, it would just get more and more and more, thicker, thicker, thicker. And, of course, you would get burned up because of the friction. But assuming that you have a way to avoid that, they use like ceramics on these probes as heat shields that will protect the rest of the probe from the heat as it erodes the outer surface of the heat shield, and it lasts until the heat shield is destroyed. But it just gets thicker and thicker and thicker until at some point you'd be like, this is totally liquid, but you never splash.
That's awesome.
Okay, let's watch this video. I wanted to talk about this before we do the video. The composition of gases, 75% by mass hydrogen gas. Now keep in mind, hydrogen gas is a very low mass gas. Hydrogen gas is 2 atomic mass units per molecule, 1 atomic mass unit per atom, but there's 2 atoms. Helium is twice that at 4 atomic mass units per molecule. Helium is monatomic. And so there's not just 3 times as many hydrogen, there's 6 times as many hydrogen molecules as there is helium, or 12 times as many hydrogen atoms as there are helium atoms. So it really is, the vast preponderance is hydrogen gas, with helium making up almost all the rest. And then you have small portions of hydrogen-based compounds. Water ice, H2O, methane ice, that's CH4, 4 hydrogens there. Ammonia ice, NH3, 3 hydrogens there. And then you have some rock there that doesn't have hydrogen. So you can see hydrogen is an even bigger component when you start including how much you have in these. I say bigger, it's not a huge amount bigger. Okay, going to the video. I can shut up for 10 minutes or so. I download it. You know what I need to do? Go to downloads and play. I don't want to play it there. I'm assuming it's going to be better quality playing it like this. Unless, of course, it doesn't play because I just downloaded it. I haven't had a chance to check. Bueno.
Voyager's grand tour of the 4 giant outermost planets marks the conclusion of man's first reconnaissance of the solar system. Jupiter, 2.5 times more massive than all
a reasonable loudness?
Saturn, its rings believed to have been born out of the collisions of long-dead moons and asteroids. Uranus, its tranquil atmosphere marred by only a few observable clouds. And Neptune, so distant from the Earth that it's invisible to the naked eye. In the late summer of 1977, 2 unmanned spacecraft, Voyager 1 and 2, lifted off from Cape Canaveral atop Titan Centaur rockets.
Yes, that was 1977.
Traveling uninterrupted through interstellar space, the Voyagers will endure forever, long after everything man has ever built has crumbled into dust. In the event the spacecraft encounter alien intelligence, both Voyagers carry a copper phonograph record, a message, celebrating the sights and sounds of Earth. Friendly wishes. These unique discs contain photographs of everyday life, as well as voices, offering greetings in 55 languages. There are also animal noises, the music of Beethoven and Chuck Berry, a baby crying, laughter, rain, and a heartbeat. All the planets in Voyager's path were in perfect alignment, something that occurs only once every 176 years. The spacecraft were in position to visit all 4 of the outer planets, a grand slam, an interplanetary home run.
This is what I consider the rocket science.
In March of 1979, nearly 2 years after launch, the Voyagers approached Jupiter, the celestial body that so fascinated Earth's first modern astronomer, Galileo. Passing through the boundary where the supersonic solar wind slams into Jupiter's magnetic field, the spacecraft's instruments recorded a strong bow shock. Named after Jove, the supreme god of Roman mythology, Jupiter is an enormous whirling sphere of turbulent gases, big enough to hold over 1,300 Earths. The Voyagers discovered thin rings of dust encircling the planet, tiny grains containing silicon or carbon, like a fine haze of ash and smoke. Jupiter's atmosphere displays a dazzling variety of alternating patterns. Cold, light-colored zones dominated by ammonia ice crystals in the higher altitudes, and warmer, dark belts of solid sulfurous particles in the lower altitudes. Voyager's cameras afforded scientists spectacular close-up views of the Great Red Spot, a storm 3 times the diameter of Earth raging in Jupiter's atmosphere. Voyager atmospheric scientist Dr. Andrew Ingersoll.
The Great Red Spot is a counterclockwise rotating storm, sort of like a hurricane, that has persisted for over 3 centuries. We were amazed that this spot could survive in the midst of all this turbulent activity.
With at least 16 known moons, Jupiter could well be considered a mini solar system. The Voyagers flew by the 4 largest, finding Callisto pockmarked by craters, Ganymede etched by icy parallel grooves, Europa smooth and icy, and Io glowing a cold and sulfurous red-orange. 9 active volcanoes were found on Io, the first observation of live volcanoes beyond Earth and Venus. These geysers were spewing hot, sulfurous gases 100 miles, high enough to hit a passage satellite. Voyager project scientist Dr. Edward Stone.
if I were to pick one discovery to represent the body of discoveries that Voyager made, I would pick the discovery of the volcanoes in Io. These were totally unexpected and really forced us to reconsider our whole concept of the evolution of small moons which are orbiting the outer solar system.
Pulling away from Jupiter after a joint reconnaissance of more than 6 months, the Voyagers got a healthy boost from Jupiter's orbit and made a beeline for Saturn. Mystifying man since the dawn of history, Saturn bears the name of the mythological god of the harvest, who reigned in the Golden Age. Traveling at more than 55,000 miles per hour, Voyager 1 arrived in November of 1980, only 12 miles off course after an interplanetary journey of more than 1 billion miles. Voyager's instruments found Saturn's atmosphere to be a cold ball of hydrogen and helium gases, racked by huge whirling storms and whipped by winds of up to 1,100 miles per hour. Saturn's magnificent rings, thought to have been the result of collisions between earlier moons and asteroids, consist of thousands of particles, swirling pieces of rock and ice, streaked like the grooves in a phonograph record. Voyager atmospheric scientist Dr. Andrew Ingersoll.
What Voyager discovered was the incredible structure in the rings. Saturn's rings are really composed of countless numbers of particles, ranging from the size of dust and perhaps larger particles the size of houses. These particles are constantly bumping into each other. These grooves are there because the rings are constantly being disturbed by satellites orbiting in with the smaller ring particles themselves.
As the Voyager swept by, sunlight penetrated, backlighting and brilliantly illuminating the splendor of the rings, like the spokes of a gigantic Catherine wheel. Voyager 1 flew within 2,500 miles of the surface of Saturn's largest moon, Titan. One of only 3 moons in the solar system known to have an atmosphere, Titan may help unlock secrets to the origins of life. Voyager project scientist Dr. Edward Stone.
Certainly one of the more exciting discoveries at Saturn was the atmosphere of Titan. It's an atmosphere which is mainly nitrogen like that here on Earth, but which contains methane, so that the photochemistry going on there today may resemble very strongly that which occurred here on Earth billions of years ago before life evolved.
By swinging around Saturn, after a close-up view of Titan, Voyager 1 was propelled out of the plane of the solar system. It is now traveling toward interstellar space. JPL project manager Norman Haynes.
At this point, with Voyager 1 out of the picture and Voyager 2 capable of going the extra distance, NASA gave us the go-ahead for a grand slam, enabling Voyager 2 to explore the last 2 giants in the solar system, Uranus and Neptune.
First detected in 1781 by English astronomer Sir William Herschel, Uranus, in Greek mythology, is the name for the heavens. 5 years and almost 1 billion miles after leaving Saturn, Voyager 2 reached Uranus in January of 1986. Like all the other planets, Uranus spins like a top, but tipped over on its side. Strangely tilted and off-center, Uranus's magnetic field extends in a bizarre corkscrew tail millions of miles into space. Its magnetic poles are also wildly askew. Voyager 2 discovered 2 new rings. Dark, narrow, thin bands of ice, rock, and dust with particles the size of a fist. Although Voyager 2 discovered 10 new Uranian moons, the most eagerly anticipated event was the close encounter with Miranda, one of the most bizarre moons in our solar system. Close-ups of Miranda revealed a strange and wondrous landscape, including a canyon 12 miles deep. Miranda may have collided with another moon, shattered, and then by the force of its own gravity, slowly reassembled itself into this chunk of rock and ice. These digitized photographs are a silent testament to the violent origins of our solar system. Approaching Neptune, after 12 years on the road and another 1 billion miles, Voyager 2 was an exhausted traveler. By August of 1989, Voyager 2 was speeding more than 40,000 miles per hour toward its rendezvous with Neptune, the last stop on its spectacular grand tour of the 4 outer planets. Discovered in 1846, Neptune was named after the mythical Roman god of the sea. The planet appears blue because its methane absorbs most of the red in the spectrum, leaving mostly green and blue. Voyager 2 flew by Neptune only 22 miles off its charted course, and only 1 second off its scheduled flyby time. Skimming only 3,000 miles over the planet's north pole, Voyager found Neptune to be a giant ball of melted rock and ice, cloaked in hydrogen, helium, and methane gases, its atmosphere whipped by winds of up to 700 miles per hour. Voyager flew the closest that any spacecraft has come to one of the outer planets, discovering at least 4 complete rings of ice and rock, 6 new moons, and a great dark spot, a hurricane the size of Earth raging in Neptune's southern hemisphere. Dr. Andrew Ingersoll.
The storm revolves around the planet every 18 hours. And then it rotates around its own axis like a big glob of pizza dough every 16 days.
Largest of Neptune's 8 moons, Triton orbits in an opposite rotation from the planet. Triton was once probably an independent object in orbit around the Sun, until it collided with the Moon and was captured by Neptune's gravity. Pockmarked by impact craters and glazed pink by a radiation blitz of methane and nitrogen ices and atmosphere, Triton is the coldest known object in the solar system and one of the most reflective. Utilizing Voyager's digitized photographs of this icy moon, scientists saw jagged mountains, high cliffs, and frozen lakes. The most bizarre discovery on Triton was the presence of icy geysers, some of which are still active, spewing organic particles 100 miles downwind. Dr. Edward Stone.
The Voyager mission to the outer planets has certainly been the journey of a lifetime. Having encountered Triton as the last world we would visit, which I don't see how any of the scientists could have been happier.
The success of the Voyager mission concludes man's first reconnaissance of his solar system. Voyager 1 is now heading toward the constellation Hercules. Voyager 2 has set its course for southwest of the constellation Sagittarius. Traveling at 10 miles per second, it is expected to pass 4 light years from Sirius, the brightest star in the heavens, 290,000 years from now. Of the 100 billion stars in the Milky Way galaxy, we barely know one, the Sun and the planets of our solar system. Yet now, courtesy of the Voyagers, we've come to know many strange and wondrous worlds. The cold volcanoes of Io, the tortured terrain of Miranda, the dazzling rings of Saturn, and the icy grandeur of Triton. These alien worlds of sub-zero temperatures, noxious gases, icy volcanoes, and multiple moons are vastly different from our own. Yet they are in many ways the same. We share the same sun. We obey the same physical laws. Yet we are unique. Our planet is the only one we know of that supports life. Voyager's breathtaking views of these other worlds have only made us more keenly aware of our own. Earth is not just another planet. It's ours. It's our home. Perhaps the legacy of Voyager, and all our interplanetary spacecraft, is best expressed in the words of the poet T.S. Eliot. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time.
As the Secretary General of the United Nations, I send greetings on behalf of the people of our planet.
Hello from the children of planet Earth.
Bonjour tout le monde. Maenaknya. Shalom. Hola y saludos a todos. Selamat malam hadirin sekalian.
Konnichiwa. O genki desu ka?
Dan PK
Genki da. I'm sure there's a button somewhere here to make it disappear. But here's my method when I'm in tablet mode. Okay, so I think that was very interesting. Obviously, otherwise I wouldn't have spent 15 minutes of class time, valuable class time. It had a lot of information in there. So now I'm going to go through some slides and try to remind you of things that we saw. Weather patterns. If you look at Jupiter, you see those stripes, and you may wonder what they are. Let's look at things that you do know on here. What things can you point out that you recognize on Jupiter? Okay. The Great Red Spot. Somebody said I, but we'll call it, it's the technical name, the Great Red Spot. The Great Red Spot's a cyclonic storm. It's basically a big old hurricane that has been going on for as long as we have observed with telescopes. Yeah.
So when I think of like storms, I think of it having like a surface to try to, form or whatever. I don't know, maybe I'm thinking too much of a tornado. And how does it just keep happening here?
How it keeps happening is, I don't think completely known. What we do know is that we have winds above and below going in opposite directions. So the winds below it are going like this, and the winds above it are going like that. And so those keep driving it. The weather patterns on all of these Jovian planets have the same basic features. First of all, these planets, because they have big, thick atmospheres, the temperatures are evenly distributed everywhere. And what difference does that make? Well, it keeps you from having the winds that go north-south so much like we have on Earth. Our winds, it's hot at the equator generally and colder at the poles, and so winds tend to, on the surface, go in toward the equator and then up in higher atmospheres go out away from the equator. And as they go toward or away from the equator, you have this thing we call the Coriolis effect, that because the rotation makes them curve, and that causes our cyclonic storms going in opposite directions, northern versus southern hemisphere. Well, you don't have that on these. And so what happens is the weather patterns are circles going around the entire planet. And so those stripes are windy regions all going the same direction, well, changing directions where you see the changing colors, basically. So you have weather patterns that are cycling around the entire planet, and so they're feeding on themselves. It helps to give them longevity. Now, the colors is another thing that everybody notices. We have names for them. They're called belts and zones. So the light regions are the zones. The dark regions, okay, what color would go good on, I don't know, are the belts. The belts are regions that have lower elevation. So it's kind of like the belt on me. The belt is the smallest diameter. The zones would be like the belly sticking out a little bit further. And because they're sticking out further, there's also a difference in temperature. Hot stuff rises, so it's hotter stuff that rises is less dense and has different state for some of its elements. That, along with the higher stuff, is going to get more direct sunlight. Those combine to give you the colors. So we call these belt zone circulation patterns. And the storms, like the Great Red Storm, come between a belt and a zone. You have winds going opposite directions, driving it. Anybody, well, you could probably have read it already. This black spot here is the shadow. The shadow of Europa. So that's not a permanent feature. That's just a moon was passing between the sun and the planet. We would call that a solar eclipse if you were in the path and you were on Earth, because you have the sun being blocked by the planet. Notice all of these little storms like this. There's lots of those. Those are all cyclonic storms of the same nature as the Great Red Spot. But they don't have the longevity of the Great Red Spot. These storms come and go. They've been observed to end. They've been observed to start. They've been observed to merge. Two storms come together and merge. So there's very interesting weather going on here. This is just a little bit about the probe. This is an artist rendering clearly. Didn't have a camera down there with the probe. You see the ceramic heat shield in front that's just been jettisoned in this picture. And it has its parachute out there to slow it down. I put this in so I could ask, is that a flat Earth? This is a picture that NASA made available from the Cassini mission that is looking from Saturn through the rings of Saturn, and then you see Earth in the background as a tiny dot. You can't tell if it's flat or not, right? You can just tell it's a finite size. But it would be kind of ridiculous, I think, to suggest that, yeah, it's just a flat pie out there. It's a Frisbee. Is it a Frisbee Earth or a pie? Okay. Rings. Let's talk rings real quick before I forget. Everybody knew there were rings around Saturn. But did you catch what other planets had rings from the video? Jupiter, Uranus, Neptune. All of the Jovian planets have rings around them. But there's a significant difference between Saturn's rings and the others. Saturn's rings are icy rings. And you have house-sized pieces and parts of the rings. The rings around Jupiter, Uranus, and Neptune are, instead of icy, they're small brown, black stuff. So it's small pieces of organic material and rock. So they're different composition. The theory is that these icy rings of Saturn were produced when comets, or a comet, got too close to Saturn, got inside what's called the Roche limit. Inside of that Roche limit, you have the tidal forces due to gravity are bigger than the gravitational force holding an object together. And so gravity won't keep it together. It will be torn apart by the tidal forces, the difference in gravitational force from one side to the other. And so if a comet made out of ice and rock mixture comes too close, it will then get shredded by the gravity of Saturn. And so that's what is believed to have caused the rings around Saturn. The rings around the other three, being a different type of material, believed to be, instead of comets, asteroids that got too close and were shredded by gravity. Yes.
So in the rings, is it like all those little parts of ice or whatever, are they also rotating around the planet, or is it just...
They're all orbiting the planet.
Yeah,
they're basically, each little piece is a moon, if you will. And as he said, they collide all the time because you have lots and lots of random motion. So all of those planets have rings. The only ones that we can see easily are the one of Saturn. And I believe the video talked about shepherd moons that guide and clear out spaces so you have gaps in the rings. Those gaps in the rings are caused by moons that are orbiting in there. And you might take the thing I just said and say, wait a minute. You said the gravity shredded it, and then you have a moon that's in there in the region where gravity shredded stuff. If the moon is not held together by gravity, if it's something like a rock that is cemented together, then it can withstand higher tidal forces, so it's not shredded. So that's how you can have a moon in the region that would have shredded a comet. Because, of course, I'm a creationist, let me bring up a creationist discussion topic. Has anyone heard creationists talk about the age of the universe, the age of the solar system, and talk about the rings around Saturn? Nope. Okay, well, I'll give you in a nutshell the argument. The argument is you have these particles going around Saturn. And because of the collisions and whatnot, they're going to lose energy. Eventually, they're all going to fall into Saturn. So the rings will only last for a finite amount of time. The rings can't last for more than like 1 million years. So the fact that there are still rings around Saturn are, according to the argument, evidence that the universe can't be that old. Is that a reasonable argument? Okay, give me your thoughts.
Sounds reasonable.
Okay, sounds reasonable?
Well, if you're concentrating things that got pulled into the orbit, then there could still be stuff being pulled into the orbit.
That's the flaw. The flaw is they're assuming that the rings can't be created by anything except for, well, what they're thinking is that a divine event is the only way they were created, that God created Saturn with its rings. But the scientific understanding is that it should be very reasonable for a comet to stray too close and get torn up and form new rings. Now, we have observed a comet get too close to Jupiter and get torn up. It did not form rings, it just fell into Jupiter. So what we observed was half of it, a comet coming in and being torn up, but it didn't form a ring. Maybe size is an issue. Maybe it needs to be a much bigger comet to create something like this. I mean, it would have to be a much bigger comet to create something like this. But there's, scientific observations that seem to support the idea that, yes, you can make these rings. So maybe, in 10 years, something great will happen, and suddenly Jupiter will have a large, let's say Qualar, okay, that's not going to happen. Let's say Pluto gets diverted and comes flying in and gets too close to Jupiter, right? Have to have a major event to change the course of Pluto. But if that were to happen and Pluto was then shredded by the gravity of Jupiter, Jupiter would have a nice big icy ring. And that would be totally cool. And then nobody would argue about Pluto being a planet or not a planet. That'd be great. Okay. Talked about Uranus and its funny tilt. With its funny tilt, tilted basically on its side, you are going to have the extreme seasons. In our activity for lab last night, you were looking at, the seasons, the last page, talking about how the angles of the sun vary from location to location, how that's going to affect the climate in different regions. Well, here, if you're on the equator, at some time of the year, the sun will be directly overhead for half the day, and then, hidden the other half the day. And then other times, it'll be on the horizon full time. Now, that's a pretty extreme change. And of course, if you're on the pole, you're going to go from having the sun directly overhead for for some time, then moving off to the side, and then being hidden for half the time. So extreme seasons for the poles. So here's a graph indicating what the seasons would be like in terms of how much sunlight you get at the poles and at the equator. And you see at the equator, there's 2 times a year when you get virtually no sunlight, 2 times a year when you have virtually full sunlight. At the poles, have a lot of sunlight for half the year, no sunlight for the other half of the year. So it's pretty crazy weather there. Looking at the interior of the planets, I know these seem really out of whack. I actually this time left them in the order the textbook had for the most part. Looking at the interior of the planets, this is what we believe based on modeling it's like. No one's been there. This is all based on modeling. Using comparative planetology? Yeah. Okay, so You see Jupiter has molecular hydrogen for a fairly thin section, then a huge section of metallic hydrogen, small section of ice, and then rock. It has a very strong magnetic field. What you don't have here is that liquid core the Earth has to make its magnetic field. Well, what conditions were necessary? There were three things necessary to make a planet-wide magnetic field. What were those three things? Okay, you had to have convection, that's one. You have to have it has to be a conducting and swirling core. So it didn't have to be metal, but it had to be conducting. Well, that metallic hydrogen is a conducting material that's swirling. It's going to have convection. Actually, I'd have to think about it. I'm pretty sure Saturn and Jupiter are both still cooling from planet formation. Just so much thermal energy from being compressed, they're still cooling. And so the liquid metallic hydrogen is believed to be what makes the magnetic field. And Jupiter has a lot of that liquid metallic hydrogen. It's swirling, or it's doing its orbits in less than half, or its rotation, less than half the time of the Earth. The distance out there is much bigger. It's making a huge, super strong magnetic field. So Jupiter is a very strong magnetic field. Saturn also has a very strong magnetic field. Not nearly as strong as Jupiter, but also very strong. Do you have a question? Okay. Now, what effects do we see on Earth from our magnetic field? I'm looking for one specific, but you may answer other ones as long as they're correct. I'll say yes, Ed. What effects do we see from the Earth's magnetic field? The one I'm looking for is the visible one, by the way. Not coming to you? Well, the Earth's magnetic field is going to deflect the cosmic rays. That is, the charged particles coming from the sun. Except if it's coming close to the poles, it spirals in along the magnetic field lines, and when it comes into the atmosphere, it causes the aurora. Aurora borealis and aurora australis, northern lights and southern lights. Now, nobody cares about the shielding from radiation because there's no life that cares about being shielded. But you're also going to have the charged particles spiraling in at the poles, and so you also have the equivalent of northern lights and southern lights on planets like Jupiter and Saturn. They're higher energy, so they're like ultraviolet, but you have those effects because of its magnetic field. Okay, now let's go on to Uranus and Neptune. Uranus and Neptune, what do they not have? They don't have metallic hydrogen. Well, as you heard from that video, they do have magnetic fields, but they have bizarre magnetic fields. The rotation axis is not exactly through the center of those planets, and the magnetic fields are not aligned with the rotational axes. So you have a planet shaped roughly like a sphere, and it's spinning about this axis, and that's pretty close to center, and its magnetic field axis is like this. What sense does that make? And the magnetic fields, now the Earth's magnetic field is not stable. The north magnetic pole drifts a little bit from day to day, not very much. A lot more drift in the location of the north magnetic pole in Uranus and Neptune. So scientists look at this, something interesting, okay? According to our theories, there shouldn't be any liquid metallic hydrogen. We have a magnetic field, so we know we have convection of a conducting material that's swirling. And it's doing weird things, not nice uniform things. And so then they're saying, well, what could be going on? And the answer that we have, the best answer we have, is that you have essentially a briny, salty water mixed in with that ice. And as you know, salt water is conducting. And so that briny, salty water is conducting, it's making your magnetic field, but because of the ice, you don't have a nice smooth flow of the water. And so it's very chaotic, and that's what causes the weirdest of magnetic fields. Very bizarre out there. Just coming back to cyclonic storms, there's a nice picture of the Great Red Spot. And you can see here lots of other storms besides the Great Red Spot. I don't know why I continued with these. That's enough of that. The winds. Winds is not the rotation of the planet. This is comparison to the rotation. And you can see that wind speeds on Jupiter are as much as a little bit over 100 miles per hour. Or, excuse me, meters per second. A little over 100 meters per second. But you have some winds going in one direction, some going the other. And if you look at those, you can see that the colors vary with the direction of the wind. So here it's dark with the wind going this direction, light with the wind going here. The wind shifts, and you have the color shift with it. So you have a lot of weather patterns with winds going different directions. Here the wind's going one direction, here it's going the other. Saturn, the winds are almost all the same direction, but the wind speeds, oh my goodness. Right, if this is 300, that's 400. It's about 500 meters per second for the wind speeds on Saturn. Saturn has really massive winds. Then you get to Uranus and Neptune, and those are like the most bizarre wind speeds I can think of. You know, big loopy things going forward and backward. So there's very interesting wind speeds. Remember I said all of these planets have the same belt zone structure for their weather patterns. But Jupiter's is much more pronounced than you see in the others. You can just barely see, like here you can see, is that a belt or a zone? It's a belt because it's the dark one. So you can see a belt right there, and you can maybe see there's some other things there. They're not nearly as outstanding on Saturn. I believe it's simply because the temperatures are much colder in the atmosphere. So you have different photochemistry. Uranus and Neptune, obviously not as outstanding there as well. Uranus and Neptune, they talked about the color of Neptune, I think. Uranus and Neptune's colors come from the same thing. It was the methane absorbing red light. And so you have slightly different concentrations of methane in the two planets, and that's why the colors are slightly different. I've got a few minutes. What's the atmosphere like on these planets? Well, as you can see, hydrogen sulfide. Anybody know anything about hydrogen sulfide? I believe that's the rotten egg smell chemical. So, okay, just so you have that for record. But you have hydrogen sulfide here on Uranus and Neptune, then methane, then hydrocarbons. Very similar atmospheres. And if you look at the temperatures, similar temperature profiles. If you look at Saturn, notice that the upper atmosphere, it's maybe 120. Jupiter's is actually pretty similar in temperature, the upper atmosphere. What's it made out of? N2H4, maybe, for the outer atmosphere of Jupiter. P2H4, maybe, for Saturn's outer atmosphere. You get down, you have ammonia clouds. Ammonia is NH3. Boy, I don't even know what to call that. Ammonium sulfide, maybe?
Yes.
And then water clouds. So you have similar types of things for the two big ones and for the two small ones. And I will stop with the pictures of Saturn. This is what Saturn looks like over 5 years. Because of our changing perspective on it, we will see the rings slowly shifting about. And so you get different views that are all cool. All right. Have yourselves a swell day. I'll see you on Friday.